Okay. Good afternoon, Ashish and Sam. There's Mr. Eric. And Eric.
Hello. Hey,
Good afternoon,
good afternoon.
Ashish, Sam, and Richard. Okay. Okay, I think I got the information. I'm going to go ahead and poll you again. Just so I'll make sure. Graduate versus undergraduate. Sam, are you a graduate or undergrad?
Graduate.
Okay. So I know what Ashish is. I know Eric is. Okay. Richard, you are, right?
This is me.
Okay. And Sam, you are. Okay. I
Professor,
think this
quick
place
question.
is great. Go ahead. Yeah.
I see we have a graduate student research assignment for this week.
I'm going to talk about that here in a few minutes. Yeah.
Okay, yeah. So just a question, would that be for every week or is it only for this week?
No, there's a paper every week. Okay.
For every week, okay.
Every week. Yeah, and I think we'll go ahead and get started. Yeah, and don't, we're not going to worry about going back to week one, week two. But in talking with uh, Dr. Donko, I basically, there was a requirement that I'll just say that I forgot to put in that for graduate students, there has to be something a little more strenuous, okay, for graduate students. And so we basically came up with the conclusion that we will have a research paper, okay, and I'm getting ready to go over that now, okay, as far as what's going to be in that research paper. And there'll be one for each week. Okay, Mr. Ball, I know you're a graduate student. Who's on iPhone?
Hello, me.
Oh, yeah.
Viewer.
Okay. Mr. Get your
Il,
last
Il, Ilbert.
name.
Yeah.
Oh, yeah. Okay. 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 Got one, two, three, four, five, six. Okay. Okay. So let's go ahead and get started. The first thing I want to do is I want to go do a share. Just kind of get you what's happening. If you just came, what I was just relaying was that where do I want to go? Screen two. No, I don't want screen two. Share. No, that's not what I want. You don't care to see that. That's my. Let's see, share. Okay, 1 second. Left my glasses. I'll be right back. Wait a minute. What do we got here? I got some. There we go. Okay. Okay. Where are you? Where are you? Where are you? Okay, so can you see my screen? Let's go back to here. Photography. Okay, do you see my screen week three? Second, I don't think you can see it.
No, I cannot see anything.
Okay. Let's share. Okay, do you see now? Week 3?
Yeah.
Yeah, we can
Yes.
see.
Okay. Okay, so I'm just gonna move down here and talk about it. So each week there's an additional for if you're a grad student, which there's 7 of you. Okay. And I'm gonna make a little bit of change to it, but what it is, we're just gonna go one step further in what you're basically doing. You're doing the homework, you're doing the assignments, you're doing the project. Okay, you're doing the Cornell notes. Okay. And what we're going to be doing in the project is basically doing a little more research that basically is going to extend, okay, what we're doing in addition to that. So what we have is, I do this. Each week you'll have assignments. So for example, for week 3, which is this week, Uh, in addition to what we're going to do, what I'm going to want you to do, again, this is only for graduate students. And basically it's going to correspond to what we're doing in a given week. So yeah, this week we're talking about symmetric cryptography, design, strength, and trade-offs. Okay, so the objective is to analyze modern symmetric encryption algorithms and their implications, which is we're going to dive into today. So in this particular one, I want you to write a 3 to 5 double space, okay, 3 to 5 paper analysis covering block versus stream, ciphers, design goals of the DES, data encryption and advanced encryption, and then the information on key size. Okay, we're going to talk about a little bit about that today. But the research on key size, performance, and security trade-offs, and then just kind of what you could find out on the common modes of operation. These we've already went over, but based on the fact that I want you to, right now it says 6, I'm going to break that down to 3. Okay. From 3 sources, find information that would cover these 4 items. Okay. Explain why algorithm misuse is often more dangerous to weak algorithms. And then in the paper from 3 different sources, and I'll update this to show 3 instead of 6. Then include NIST and standard-based references. Okay, look that up. Okay. I'm also going to be doing this as part of the research. Anything that you don't understand, okay, I want you to look it up. And if after you look it up and still don't understand it, get with me. And I'm doing this for a purpose. I'm doing this because as a graduate student, you're going to be running into terms and processes, okay, that you may be seeing for the first time. Okay. And I want to get that kind of instilled in you guys that you know that, yeah, part of what I'm going to do as a graduate student is I'm going to need to research. Okay. So that's why there's some of the terms here. If you don't know it, look it up. Okay. Understand it. If after you look it up, you still don't understand it, okay, then yeah, get with me. Okay. Any questions on the general overall? There's a different one for each week. Okay. This is for week 3. Yeah. Again, 3 to 5 page per paper. Yeah. Any questions on the paper? Are we good?
No.
Okay. Go ahead.
What type of format do you want the essay to look like? APA, MLA?
Again, I'll leave that up to you. Okay.
Okay.
Okay. I'll leave that up to you. Mm. So
Okay.
yeah, I'm not really not looking for all of you to give the exact same format necessarily. Okay. So no, just as long as it covers the specifications in the assignment. Anyone else? Okay, so with that, okay, so with that, that's basically going to be covered down again as far as another piece of coursework that you're going to be needing to do beside the assignment, the Cornell notes, the project, and the quiz. Okay. Again, because you are graduate students, the expectation is that you need a little more rigor. Okay. 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 So let's go ahead and continue on. And what I want to do is let's unshare this and let's share this. Okay, everybody should see week 3 cryptography. Okay. Okay, they talk about prime numbers, modular arithmetic, and RSA. When we first started up the class, we stated that I'm gonna do that. That the cryptography uh, uh, basically the cryptography programmings that we use, the programs that we use, okay, were basically based on transportation, okay, or substitution. But we also said that the modern crypts that we're going to be going through are excuse me, are basically going to change, are basically based on numbers. Mhm. So what we're going to do is kind of do a somewhat dive into what does that mean. We talked about having prime numbers. We talked about RSA a little bit in ECC. So we're going to do a deeper dive into uh, those particular items. Okay. So with that, opening up, okay, we talked about cryptography is what it is and what it is not. We're going to go do a deeper dive. Cryptography isn't magic. It works because of mathematics. I'm not looking for you to deep dive into mathematics yet. I think there's one of the assignments that actually does that. But what it is what we're attempting to do, as with anything, is we want to make it easy to compute in one direction, encryption, but make it difficult to bring it back or do the reverse, decryption. That's our main goal, okay, with this. Okay. So today we're going to talk about two mathematical ideas. And again, I wouldn't think that this, as far as the prime numbers, anyone is not surprised yet. I'm pretty sure that you had it. But prime numbers and modular arithmetic is what we're going to touch base first. So in public key cryptography, especially RSA and elliptical curve, okay, we'll be diving into that. By the end of the class, I want you to be familiar and understanding the logic, okay, in keeping data secure. So part 1, primary numbers and why cryptography loves them, okay. A prime number, I'm going to assume that you don't know. So I'm pretty sure you do, but I'm going to assume you don't know. A prime number is a number that's greater than 1, okay, and has exactly 2 divisors. You can divide it by 1 or you can divide it by itself. Okay. It cannot be divided evenly by any other number. So in the case, just for an example, prime number is 2, 3, 5, 7, 11, and 13. Okay, I can divide it by itself, okay, and by 1, but I cannot divide it evenly by any other number. Non-primes, 2, 4, 6, 8, 12. So we have prime numbers and we have non-prime numbers. Multiplying 2 large prime numbers together is easy. And when we say, I have a number that's 2 to the 8th power, okay, a prime number, and I multiply it by another prime number, 2 to the 8th power, okay. I'm going to get a very large number that the results of it is going to be difficult for someone to try to figure out what that encrypted number? What did I use to get that encrypted number? And that's our goal, is to make it difficult for individuals to look at your key and kind of basically figure out how they can break that key by just looking at it. Okay. So here we're going to multiply two large numbers together. Okay. Yeah, factoring results back into prime numbers is very hard. Being balanced, easy forward, hard backward is the backbone of cryptography. And again, if there's a question coming up anytime, just let me know. Okay. Okay, easy to mix. And the example given here is easy to mix blue and yellow to get green, but it's very hard to unmix green to get blue and yellow. Okay. So it's kind of an example of what ultimately we're going to be trying to do. Okay, modern cryptography depends on this imbalance. Modular arithmetic, clock math. Cryptography does not use the word arithmetic. It uses modular arithmetic. And basically, modular arithmetic says I use the mod functionality. So the mod functionality says it's going to cause me to wrap around. So if we have a mod n, this says what is left over after I divide by n. So if I had a number 10, okay, and I mod it with 3, okay, I would have 3 going into 10 3 times with a remainder of 1. The mod is this particular value for 3 and 10 is equal to 1 because that's the remainder. So here we talk about modular 12. Okay, here we're taking 10 plus 5. Okay, the modular is equal to 3. Okay, not 15, because the clock resets after 12. This is a 12-hour clock. So if I have 10 o'clock and I added 5 to it, then what I will end up is 3 o'clock, okay, in the morning and not 15 because the clock resets at 12. So that's 10 plus 12 mod 12 plus 5, 10 plus 5 mod 12 gives us 3. Okay, always stays in the range of that modular number. Okay, basic modular operations. Okay, you can do modular arithmetic. 7 plus 8 mod 10 is equal to 15 mod 10, which is equal to 5. Modular subtraction. 3 minus 7 mod 10 is equal to minus 4. Okay. But here, when I mod it to 10, I'm actually going to get a value of 6. So I go up from minus 4 to 0, and then from 0 to 6 is going to basically give me the 10. So we wrap around to stay in a positive state. Modular mathematics, same sort of thing. In this particular case, I'm doing a mod 11. 4 times 6, 24. Mod 11 will be 24 mod 11, which gives me the value of 2. Okay. Now, think about it, and you'll see here in a little bit that I can get to the same number different ways. So when I do this modular arithmetic, the fact that I get 2 doesn't tell me from whence that 2 came. Okay. Because I can take 2 numbers, do a modulation on it, and get the same value. So once I see that number, it just says nothing about how I got to it. Okay, without knowing the process that I went through. Okay, these operations are predictable, repeatable, reversible only with the right information. I have to know how I did things in order to figure out that I take this key and I'm able to decrypt it without knowing the process itself. Okay, RSA, we kind of briefly talked about that. We're going to talk about the deep dive again. So let's connect the mathematics to RSA. RSA is named after its inventors. The inventors are Rivest, Shamir, and Adelman. And it's one of the first practical public key cryptographic systems. Okay, RSA is a public key cryptographic algorithm that uses two mathematically linked keys. A public key to encrypt data and a private key to decrypt it. Yeah. Its security is based on the difficulty of factoring very large prime numbers. As I said, I'm going to take a very large prime number, 2 to the eighth power, or 2 to the 102nd power, and I'm going to multiply it by an equally bigger number, prime number, and then from that, I'm going to get a mathematical key. And that is going to basically be my key that I'm going to be using in order to do the encryption. So here we're talking about private key to decrypt. It's security based on the difficulty of factoring large numbers. Makes it easy to encrypt. Okay, that multiplication process is easy, but extremely hard for attackers to reverse the process without the private key. Okay, what does it solve? Okay, RSA. It solves secure communications without sharing the secret key ahead of time. All the other processes we talked about, one of the things we had to worry about was how do we get the key to the receiver so that they can basically decrypt the information. RSA takes care of that. Okay, and we'll be walking through that here in a second. We don't have that problem with RSA. Okay. Okay, RSA has two keys. It has a public key shared with the world and a private key kept secret. Excuse me. One of the key locks, the other key unlocks. So in this case, here's the conceptual flow. We choose two very large prime numbers. We multiply them together. This product becomes part of the public key. And the public key, when it says it's public, it's really public. Anyone in the world can get a hold of that key, and it doesn't matter, okay, that they have that public key. Okay. We multiply them together. Okay, this product becomes a part of the product of the public key. We use modular arithmetic to generate a public key component and a private key component. Okay. We publish the public key for anybody that's going to be sending us information, but we protect the private key. So no one knows about the private key. Now, the key thing with this is that the public key everybody has. The private key only the owner has. Okay. So basically, we're working on the basic idea that you need to send me some information. Okay. So with that information, okay, I'm going to tell you the public key I want you to use to encrypt it. I give you the public key, you encrypt it using that public key, and you send me the file. Okay. Yeah. I know that based on that public key, I have the private key that's associated with it. So once I receive information, I basically am able to decrypt it because of the fact that I and only I have the private key. Okay. That's the basic of RSA. Okay. Uh, Being the fact that the attacker cannot factor the two numbers, they can't derive the private key. That's the key thing. But here, encryption uses the public key and modular exponentiation. Decryption uses the private key and modular exponentiation. Same math,
Yeah.
different keys. Yes, go ahead.
But how are you gonna share the private key?
We don't.
How the other party gonna have know the private key?
Okay, the way it's going to work is that uh, you want to send me some information, right?
Yeah. So I have the
Okay.
public key,
Yeah,
and
you have the key that says, I want you to encrypt using this key.
so the public key is available for everybody.
Anybody.
Yeah,
Doesn't
but
matter.
but the private key, how I will send it from my side to your side.
Okay. We don't. We don't. We said, when we look at this here, we said basically I'm going to encrypt using, you're going to encrypt using a public key and some modular exponentiation. Okay. We're going to give you a process to do that, to encrypt it. Okay. You want to send me, I need secure information. So I'm going to give you the public key to use.
Yeah,
Okay.
but when the time comes to decrypt it, when you receive it,
I receive it. Okay.
yeah, how are you gonna decrypt it if you don't have the private key?
I know I do have the private key. I have it, but those people who are sending me the file do not have it.
How did you get it at the first place?
Okay. I basically went through the process here of taking, let's go back. We'll go here. Yeah, here. Okay. So here we have the conceptual flow. We choose two very large prime numbers. We multiply them together. This product becomes part of the public key. We use modular arithmetic to generate a public key component and a private key component. So I'm basically building my keys right now, okay, with this. I'm building my keys. I'm building a public key and a private key. I publish the public key. So if you have information that you want to send to me securely, okay, you're basically going to encrypt it using the public key that I gave you. But this public key, because it is part of, I have a public key component and a private key component that came out of this arithmetic. I'm the only one who has the private key. So when you send me something, it says, okay, I'm sending you this information based on the public key that you told me to use. Okay. When you send me the information, I can decrypt it because the public key I gave you is based on the mathematics where it used the public key and the private key. Does that make sense?
So you mean when I send that information to you, I encrypt it with my public key.
No, not with your public key, with my public key.
With your public key.
Yes, with
Not
my
my
public
public
key.
key.
Not yet.
So
You
everybody who sends any information, he encrypted with the public key of the receiver.
correct, correct. Of the receiver.
And the receiver, he gonna be know that it's decrypted his public key, so he's the only one who can decrypt it with a private key.
Correct. Because the private key and the public key came from that algorithm that based on these two huge prime numbers, okay, was able to, we did the process on creating it, and then we out of that came out with a private key component and a public key component. Okay. Two
So
pieces.
how we gonna ensure the integrity or the security that nobody gonna send us unauthorized messages? Since now in this scenario, everybody can use our public key to send us information.
Okay. If someone tries to send information that wasn't created with the public key, then it won't decrypt.
No, what I meant now, since everybody
Right.
now have the public key for everybody, maybe a third party that is not allowed to be like there, he gonna be using their public key to send them information.
That means it's not secure. Like that's what he's trying to say. Oh,
No, if I may,
Go ahead.
even if a random party gets the public key and sends it data to you, the filtering part needs to be done at your end, right? So even if let's say an unauthorized user gets a public key, gets a hand of a public key and he sends you some data which is, let's say, rubbish, you can just do the filtering at your part and just eliminate it. Getting a hands on a public key doesn't mean your system is compromised. It just means
Correct.
that you will get some random data which you can filter at your end. Public key, when the system says publish the public key, I don't think it means just throw it in the internet and say, oh well, this is my public key. It means you give it to a protected client. But if anyhow it slips out, it's not a big deal. You can just filter it at a time. Is what I think. And
No,
it's
no,
how I've been using it.
you're right. When you're, and again, this is not this an arbitrary. We know that you have some information to exchange, or we have information to exchange. Okay. What the public key allows you to do, it says, here's the key I want you to encrypt with. If somebody got that information, okay, and send it to their friend couldn't decrypt it because the friend doesn't have the private key. Okay. It doesn't matter that someone else got the data. If they don't have the private key, they're unable to decrypt it. But you're going to be talking, you're going to be working with the individual that you're basically be exchanging information from and to. You know, I have a company ABC, you're going to be sending me some employees' names, okay? Okay, and you'll say, okay, well, yeah, I need to send you this information. I will say, okay, I'll calculate and figure out what my public key is, what my private key is, and then I'm going to send you the public key. Here, I want you to encrypt it based on this. You will basically encrypt it, send the file to me, okay? If for some reason you accidentally send the file to company C doesn't have a private key, so they won't be able to decrypt it. I'm the only one who can because I'm the one who gave you the public key.
So the private key, we just have just one copy, I think. Yeah, so everyone has just one. So if someone wants to send me, if I want to send someone data, so he should give me the public key, own public key, created by him. So I mean that in this situation, so we just have one copy of private key. You don't give it to anyone else, I think.
No, and that's true. You're not going to just arbitrarily put that public key out. But what it's saying that if someone else in the public arena got that information, it really wouldn't help them. They could not decrypt it. Okay.
Yeah. No, I mean not public key, private key. Sorry, I mean
okay.
so you have the private key, so you cannot to send it. It's not secure to send the private key to someone, I think. Yeah.
Okay.
So if you want to communicate like in the worst way, you should also take the other's public key, so they cannot use your private key to send data. They also should create their own public key. After that, you will send data them using their public key, and they.
If there's an agreement that we need to say verify information, you want to send me this file, I give you my public key, you encrypt it, I get the file, I decrypt it, I send you a confirmation back, okay? You send me your file and you send me the file and you send me your public key. So once I get the file, I'll send the confirmation using your public key, I'll encrypt it. I'll send it back to you. You have the private key for the response. So you will decrypt it to make sure we have a confirmation. Okay. So it's all based on the fact that the receiver, okay, is in control. Okay. The receiver is in control. This receiver puts together the public key, and this receiver is the only one who has the private key. So we get away from that need of having to transfer the key that's going to decrypt the information. We don't have to worry about that anymore because we're the one who's sending it. Does that make sense? Is that something that's still confusing?
Yeah, it's like when you want to talk to somebody, tell him if you want to talk to me, use this number or this key or this code. So,
Now, which key? Okay.
like when you talk to somebody, tell them that when you want to talk to me, give me this code or like this me this symbol, and I know that this you are talking to me because you're the one who told them that if you need to send me a message, take this hint.
Now let's make sure you understand that when I send that public key, okay, that's not the same key I'm going to be using forever. Okay.
It
Yeah. If
change.
right, if we have information that we need to exchange, okay. Today my public key might be 123A5. Okay. Okay. In which when I give it the file, I'll decrypt it. Okay, tomorrow I'm going to use a different public key. Okay. I'm going to use a different public key. So in normal business transactions, we're not going to have the same public key. Okay. Every time that I'm getting ready to pass information. Okay. we'll still have it. But again, what it basically does is it says that if for some reason someone got a hold of the key other than who I'm supposed to be receiving information from, that individual or that company or that entity won't be able to decrypt the information. Now, you might have an argument to say, okay, well, what's preventing someone from sending me information for the private key? I mean, for using the public key. Okay. Now, that's a possibility. If for some reason you sent me information, okay, and I sent you the public key, but for some reason you gave it to your partner, okay, and said, okay, here's the public key. The only thing you could do with that public key is send information encrypted by that key. And so you have to know the encryption process and you have to know the key itself in order to send information. Yeah. Now, again, sending that information to anyone else other than me, because I got the private key, goes nowhere. You cannot take that key, encrypt it, and say, here, company two, here's some information that we're getting ready to send to the receiver. Here, you can have it too. Because it doesn't do anything because you don't have the private key.
Yeah, I know, but what I was trying to say, if the other partner send it to you,
Hmm.
how are you gonna know that it's coming from me, not from my partner? Because now both of us had the same public key that you shared with me at the first place.
Okay. And we're going to cover that. Okay. So remember we said that one of the things as far as cryptography is that you have to have authentication. Okay.
This is what I'm trying to say, because if like me, we are trying to communicate, but maybe the other partner is not communicating or sending malicious messages. So how you know it's not me?
Uh, about
Yeah.
that,
Okay.
I understand what you're trying to say, but you are trying to compare RSA with the communication model. RSA doesn't really work on you going back and forth and communicating with the whatever I say, let's say a recipient or something like that. It's more like it just ensures that the data the sender is sending is not tampered with. It doesn't really see whether the sender is what do you say, like the intended sender or not. You send the public key to some people, even if it gets leaked from their end. It just RSA just ensures that the data that the sender is sending is not tampered with. It doesn't work on seeing whether the data is correct coming from a correct user or not. That part, as Sor said, works on the authentication part that you're gonna do at your end, where you will see because when the sender sends a data, it doesn't just send the data. Say, let's say you are sending a message hi to me. So the message doesn't only contain hi, it contains your some kind of information like an IP address or something. Everything is encrypted. So authentication at your end confirms whether that this is the correct party or not. If it's not, it'll just throw it out. So by securing data, it doesn't mean it secures the user. It just secures that the data that's getting transferred is not tampered with anybody else in between. That's the only purpose of RSA is. What you are
And
trying to
remember,
achieve
you're not.
is,
Oh, go ahead. Go ahead.
sorry,
Finish.
what
No,
you're
no. Go
trying to
ahead.
achieve is what you get from authentication, where you check whether the data you have received is from the correct user or not. So that's what authentication does, and what RSA is totally different. It just makes sure that the data user is sending is not tampered with in any how in the middle person.
And with that, think about the timing. This is not a situation where I'm going to give you the public key, and then next week I'm going to send you a file. Okay. Assigning the key is part of the send process. Okay. Okay. Part of the key. I need a file I need to get to you. I need a file that I need from you. When I call you up, immediately I'm saying, I'm ready for your file. Here's the public key. Okay, here's the public key. You basically encrypt it. You send the information to me immediately. It's all part of one process. Okay. So it's not like that what I'm doing is getting a public key, waiting till tomorrow, then sending the data, and then sending it to you. that process is one continuous process where I have data to send. Okay. I will ask you for a public key. You will give me the public key. I'll do the encryption. I'll send you the file. And based on the public key that you created, I have the private key already on my side. I'll decrypt it and I'll give you some sort of confirmation. Okay. It's all part of one process. Okay. There's not a really, can somebody get a hold of the key? Okay. Yes, but because it is part of one process, part of that sending process would be that once you have sent the data, okay, that public key is no good. Okay. I can just disable, say, I'm not using that public key anymore.
Okay. Understood.
Okay, because it's all part of that process. Now, I'm not going to use the one I created today is probably not going to be the one I'm going to use tomorrow. Okay.
Yeah, and sorry, I just
Oh, no,
want
no, go ahead.
something else too. Like a quick example of it, I believe it can be like when you try to connect to your TV light, right? When you try to connect to YouTube through your phone. You know how YouTube throws this code that you put on your phone, this random code that's always different every time you ask it, like, hey, enter this code to the app, and then it connects to the TV. So that code can be seen as the public key. It just generates a different number
Mhm.
every time so that no
That's
one
OTP,
Mhm.
one time password.
Yeah.
yeah.
Yeah. Yeah. Yeah. So, but again, it's public in that if someone else got a hold of it, so be it. Okay.
Yeah.
Okay. Does that make sense?
Yes.
Okay. So to do private key. Okay. Using Cree. Okay. We got that. Okay. Just as far as the large primes. Okay. Uh, so here, there's a space they talk about what do we call a large prime. RSA uses keys that are 248 bits. 1 second here. Hmm. Sorry about that. Right, Nicole. Okay, but the actual RSA key that we're going to be using in order to compute the public and private key, they are usually 2048 bits or 3072 bits or larger. Okay. Uh, so that you're looking at that, the number of possible numbers, or permutations I can get at that is 2 to the 2048 or 2 to the 3072. Okay, so those large prime numbers, okay, are basically what is being used. We're talking with RSA, we're talking big. Now with big, you have additional processing in order to get it to work. Okay. But the keys here is trying to figure out what combination of 2 to the 2048, what part of that, what combination created the key is almost impossible. Okay. So RSA secure. Uh, the downside is, we have to do computations, whether we're doing multiplication, division, addition. That's extra time that we're doing are required for us to be able to figure out what the key is, or figure out what not only what the key is, but what the private key is, and then what the public key is. Both of those are going to take time in order to do it. And because, again, we're using mathematics, we have slower key generation and, of course, larger key sizes. Yeah. Okay, this leads to a new approach. Okay, this is what we just talked about here. I did insert this in here as far as the question of how does the private key get to sender, and what we just talked about is they already have it. Okay, okay, they already have it. So this is what we just talked about. Okay, now I did want to go over this analogy to kind of clear things up. The analogy here is kind of fits very nicely. So imagine you had a receiver that builds a padlock and keeps the key. They mail out the copies of the padlock to everyone who wants to send data to them or sends them a message. Anyone can lock the box, but only the receiver can unlock it. Okay. The key, private key, never travels. We never move the private key anywhere. And think of that as a padlock that the sender just sent out. You can lock it, okay, and anyone can lock it, okay. But when the receiver receives it, they're the only one who has the key to open that padlock. Yeah, and this is just what we just talked about. I think the common thought of is when we first said is that the common thing is we think that we have to send the private key. We have to send the key in order for this to work, but we do not have to send that key. Okay, one of the things that's a little better than the RSA is the elliptical curve cryptography. The concept here is that for ECC solves the same problem as RSA. Secure key exchange, encryption, digital signatures, but but it does so more efficiently. Okay. What does this digital signatures do for us?
Make sure it's us. It authenticates it.
Okay, yeah, it's part of the authentication process. We were talking about how do we know that someone sent something uh, that I'm expecting. Okay, and I'm not getting information. And we do that basically from digital signature. Okay. And can treat digital signature just like we do, the RSA, and we can encrypt it, decrypt it. We can send the signature, have a key in order to unlock it, but excuse me, have a key that will be able to encrypt it, but not have the key in order to decrypt it. So the same process we can apply to digital signatures, so someone can't forge a digital signature. But we can have more efficient. The thing about the ECC is that it's based on mathematical properties of the elliptical curve. Okay, not getting into exactly what that is, but think of that you have an arc. Okay, that you have an arc, and based on where you fall down on that arc, that is going to determine what your key value is. Okay. So rather than doing modular arithmetic, we're doing elliptical curve arithmetic. There are points on the curve, okay, is what we're doing. Difficult to reverse problems. You don't need to know the equations that we're going to talk about. This is probably one of the things that, as far as a graduate problem, how does the elliptical curve work? Yeah, that would be a good one. So you don't need to know the equation, just the idea. ECC creates a problem that is even harder to reverse than the factoring of large prime numbers. Okay, difference between ECC and RSA. RSA is based on factoring. ECC is based on elliptical curves. Needs very large keys in order to work. ECC can use smaller keys. RSA, because we always have these computations on those large keys, it's going to be slower than the ECC. More computational overhead, okay, more efficient. RSA is older. ECC is more modern. RSA 248-bit or ECC 256-bit are the standards. Okay. Massive efficiency gain. Okay. I think one
Sorry,
of your, go ahead.
question.
Uh-huh.
I'm so sorry.
Clear.
When you say RSA slower and ES like the elliptical curve is faster. What do you mean by that? Like it's slower to make the key, or it's slower, what exactly? To generate the key?
Right. You have to go through computations, okay, to generate the key,
Okay.
right? Okay. And multiplying, say just what is, let's keep it simple. Okay. Let's say we had our key length was 5. Okay.
Okay.
Okay. So that's the number of keys we can generate is what? 2 times 2 times 2 times 2 times 2. 2, 4, 6, 8, 10. Okay. That's 10. Okay, so I can get 10 possible keys out of that. Okay. All this is saying is RSA is I have to do that computation.
Okay, okay.
It takes time for me to do that computation. And it's going to take more time for me to do a key length of 10 to a key length of 100. Okay. It's going to take me more time to do a key length of 1,000. Okay. Yeah. The bigger the key, the longer it's going to take me to figure out the computation.
Okay, okay. All right. Yeah, I was
Okay.
just wondering that.
No. Good question. Okay. And just ECC, not deep diving into the mathematical background, basically is saying that what we're doing for pinpointing a point on the curve is going to take less time than what it's going to take for us to do a computation on a number that's millions of bytes long. Okay. So that's what the particular comparison is doing. Okay, so ECC is widely used, module devices, mobile devices, HTTPS, blockchain systems, IoT transmission, anywhere where we have to encrypt things and need to do it quickly. Okay. Kind of wrap up, what should we walk away with? You should really explain why prime numbers matter in cryptography, what it buys us, perform modular arithmetic, RSA, conceptual level, understand why prime numbers are essential. I believe, let's go through the lab. Where are you? Okay. Looking at the project. That's week. Yeah, week 3. Okay, just want to kind of go over the project real quickly. Okay, as far as the project for week 3, okay, what we're doing is basically using the information we just talked about for the RSA. Okay, so here we're going to be implementing the RSA to kind of give an understanding for modular arithmetic. Okay, we want to learn perform modular exponentiation. So we said this term. Now, what does that actually mean? understand the idea of a modular inverse, use the concept of big I and T. Okay. What's big I and T? There's a similar
Big integer.
yeah, okay. Every language, whether it's C++, Python, Java, okay, you have the big integer. And when you multiply two big prime numbers together, you're going to need something that's bigger than the standard field holders. That's where the big integer comes in. So basically using that and prepare for RSA implementation next week. So you're doing VS Code, we're doing a math.js and AP.js. Okay. And this is basically the logic. Okay. Again, what I want you to do as additional information is do a line by line analysis of what this is doing. Okay. Okay. Line by line, have chat do you a line by line analysis of what's happening in each way. So when this is kind of looking at, we stated we wanted to do some modular exponentiation, but we really didn't say how. This is kind of breaking down what that how is. Okay. And so by doing a line by line analysis, you can see what is the detail, what are the steps we're going through in order to get that RSA key. Okay. So it's kind of the same. Doesn't take long, probably all of 5 to 10 seconds to get that information on a line by line analysis. So we got the math.js, which is the math part. Here's the actual execution part. Here's the code that goes with accumulating that. Run math.js, run app.js. Okay. And then give me a screenshot of console results. Subject question, why do we need modular exponentiation for RSA? Looking at how and what it's doing, okay, could help you with that answering that question. Okay. And so, and why do big IT necessary for JavaScript for cryptography? Okay. Again, having to do with the numbers we're multiplying. So that's kind of the overview of RSA. If you really want to, I didn't really put it as extra credit, but if you wanted to do the corresponding ECC process, look that up and say, give me code that will calculate the ECC, and then you can do a comparison of the RSA with the ECC, okay, to see why ECC might be better as far as the key length and the internal processing when you do a line by line analysis on the ECC. Okay, again, not part of the project, but something that you might want to do just to get that comparison. Okay, any questions?
About this now.
Okay. Okay, if not, well, give you 15 minutes. And hopefully we'll see you next Monday, next Tuesday. But they're talking about snow again on this weekend. So, but
Uh, I sent you the picture of the project of the first week.
mhm.
It was corrupted, but you said me sending you the picture again in order to fix the grades.
Yeah, I have not looked at. After I get off of this, I'll be looking at the cryptography. Okay, so you said you did send it.
Yeah, I did send it. You told me to send that picture because the picture was
Okay.
corrupted. I did send it last week.
Okay. Yeah, I'm getting ready to grade those shortly, right after I get off of this meeting. Yeah. Okay, everyone, have a good one. Any questions in going through the homework or the project or anything like that? Oh, I did want to say this, that one thing to keep in mind is that which may be kind of an incentive to maybe do the RSA and ECC analysis, go ahead and program that. Is at the end of the semester they have according to Dr. Danqua, a project presentation. Okay. And I think the whole university gets involved into it. But he was saying it might be a good idea from both my OOP class and cryptography class that some of the projects you're working on, you put it together such that you're ready to present it to part of the additional faculty. Okay. So be thinking about that. Okay. That what you're doing, uh, how you spruce it up, or what additional things you might want to do to it if you were going to make that a presentation to the university on a whole and not just for this course where I'm the only one that's looking at it. Okay. So be thinking about that because I would like to have some of the project information that you're using in this class and kind of maybe spruce it up a little bit and have it during that presentation time period. So thoughts too. And everyone here, I have no problem. I know that you guys are able. Yeah. Okay, if that's it, I'm going to call it a day and get in touch with me. Okay, did someone else come that I did not down here? Got Mr. Barr, got Ashish, got Rick, got Eric, got James, got Imrat, got Sam. 1, 2, 3, 4, 5, 6, 2, 4, 6. Who am I missing? I can't forget. I have one more, thought there's 7. Okay, so we're good. Again, let me know if you have any questions or issues. See you on next Tuesday in person.
See you.
See you, teacher.
Bye.
Yep. Thank you for showing up.